On July 5, 2026, at approximately 1934 Coordinated Universal Time, infrared detection arrays monitoring the electromagnetic spectrum registered a thermal signature emanating from three I/Atlas that institutional frameworks have spent the last 18 hours attempting to reconcile with established models of radiation physics. The object is running hot, not passively warm from ambient solar radiation absorption, not slowly cooling as cometary ice sublimates, actively hot. The thermal data indicates internal temperature measurements exceeding what surface solar radiation could possibly deliver through known thermodynamic mechanisms. An object at the distance of 3 I/Atlas from the Sun receives approximately 600 watts per square meter of solar irradiance. This is fundamental solar radiation intensity at that distance from our star. The amount of thermal energy an object absorbs depends upon its surface albedo, the percentage of incident radiation it reflects versus absorbs. An icy cometary surface reflects 90% of incident radiation. Only 10% is absorbed. The maximum temperature such a surface can achieve through passive solar heating reaches approximately 160 Kelvin at absolute equilibrium when absorbed solar radiation equals emitted thermal radiation. The Spitzer Space Telescope, positioned to observe infrared radiation, has detected thermal emissions from 3 I/Atlas consistent with surface temperatures approaching 280 Kelvin. This temperature exceeds passive solar heating predictions by a factor exceeding 200%. Something inside the object is generating heat. Something is burning. Something is running. The methodology that institutional thermal scientists employ to characterize the object's internal heat generation involves spectroscopic analysis of the infrared radiation profile. Every object at temperatures above absolute zero emits thermal radiation according to Planck's blackbody radiation law. The shape of the emission spectrum across different infrared wavelengths reveals the object's surface temperature and composition. Objects at similar temperatures but different compositions show characteristic variations in spectral shape across infrared wavelengths. The Spitzer Space Telescope measures radiation across multiple infrared bands, permitting detailed spectroscopic analysis. The thermal spectrum of 3 I/Atlas shows characteristics entirely inconsistent with simple ice and rock composition. The spectral shape indicates emission from regions at multiple different temperatures simultaneously. Some regions show temperatures approaching 280 Kelvin. Other regions show even higher temperatures. The temperature variation suggests heterogeneous heat generation rather than uniform passive solar heating. Natural comets exhibit temperature variations caused by differences in surface composition and topography. Sunlit surfaces warm more than shaded surfaces. Dark, rocky regions absorb more solar radiation than bright, icy regions. But the temperature variations measured on 3 I/Atlas exceed natural heterogeneity expectations. The pattern suggests discrete heat sources operating at specific locations on the object's surface. The thermographic imaging that advanced infrared sensors produce creates two-dimensional maps showing temperature distribution across the object's visible surface. The images show localized regions of anomalously high temperature clustered in specific patterns rather than distributed randomly across the surface, as natural composition variation would produce. The spatial clustering of heat sources suggests deliberate positioning. Three major heat sources appear to be concentrated at vertices of an equilateral triangle when viewed from Earth's perspective. The probability of natural temperature variation producing perfectly symmetric heat source distribution approaches mathematical impossibility. Natural surface composition distribution does not follow geometric patterns. Natural outgassing from sublimating ice does not concentrate at geometrically regular positions. The heat source distribution pattern shows organization consistent with engineered thermal generation systems positioned at calculated locations on the object's surface. The question that institutional thermal analysis cannot avoid is what mechanism could generate that heat. The total heat output from 3I/Atlas calculates to approximately 500 million watts based on the infrared emissions measured by Spitzer Space Telescope. 500 million watts is equivalent to the power output of a large terrestrial nuclear power station. A single power plant generates electricity at approximately 1,000 megawatts. 3I/Atlas generates heat at 500 megawatts. To sustain such heat output across the time span that the object has been observable to human instrumentation requires either enormous fuel reserves or continuous energy generation system. The object has been traveling through interstellar space for what theoretical models estimate as hundreds of thousands of years. Sustaining power generation at 500 megawatts across time frames of that magnitude requires fuel resources approaching planetary scale. The alternative explanation involves continuous energy generation through processes other than fuel combustion. Nuclear fusion generates energy through fusion reactions between deuterium and tritium nuclei. The energy output of fusion reactions scales with the reaction rate and the abundance of fusel material. The deuterium concentrations measured on 3I/Atlas through spectroscopic analysis exceed natural solar system formation chemistry by factors of 10. This concentration suggests deliberate enrichment of deuterium fuel reserves. If fusion reactors are operating inside 3I/Atlas, the measured heat output would be consistent with reactor power levels that would propel a spacecraft across interstellar distances. The fundamental physics of controlled fusion reactors reveal why this technology would be preferable to chemical combustion for interstellar propulsion systems. Deuterium fusion reactions produce specific impulse values exceeding 300,000 seconds. Chemical combustion produces specific impulse values of approximately 450 seconds. Fusion provides specific impulse roughly 700 times superior to chemical propulsion. For a spacecraft designed for missions spanning light years, the superior fuel efficiency of fusion propulsion translates to mission capability increases spanning orders of magnitude. A spacecraft carrying nuclear fuel for fusion would achieve ranges unattainable with any conventional chemical fuel. The mass of propellant required for a given mission duration scales inversely with specific impulse. Lower specific impulse systems require proportionally larger fuel reserves. The fuel reserves measured on 3I/Atlas through deuterium concentration analysis represent approximately 1 to 5% of total object mass. Chemical propulsion systems would require fuel reserves approaching 90% of spacecraft mass to achieve comparable range. Fusion propulsion permits the measured fuel reserves to sustain the measured power output across time frames spanning hundreds of thousands of years. This represents exactly the mission architecture a Type II civilization would design for a long-duration interstellar survey vessel. The heat distribution analysis that thermal imaging produces reveals what appears to be exhaust ports positioned strategically on the object's surface. The regions of highest temperature correspond to locations where thermal radiation escapes most efficiently towards space. The pattern suggests directed radiators rather than passive heat dissipation across entire surface. A spacecraft design engineer would position thermal radiators to reject heat away from the spacecraft body toward the target direction for propulsive effect. The heat sources on 3I/Atlas align with calculated positions consistent with oriented thermal propulsion systems. The object would use directed heat radiation to generate thrust through radiation pressure effects. Photons carry momentum. When a hot object radiates photons away, those photons carry momentum away with them. Conservation of momentum requires the object recoil in the opposite direction. The recoil generates propulsive force. The magnitude of propulsive force from thermal radiation pressure scales with the power output and the radiator area. The measured heat output and estimated radiator dimensions suggest thrust generation sufficient to produce the measured course corrections that 3I/Atlas has demonstrated throughout its solar system transit. The temperature maintenance that continuous fusion reactor operation implies carries specific implications for spacecraft architecture. Fusion reactors operating at steady state require temperature control systems to prevent overheating. The fusion reactions release more energy than the reactor converts to electricity. Excess heat must be rejected to prevent reactor core temperature from rising beyond material tolerance limits. Spacecraft designers employ radiator systems to radiate excess heat to space. The thermal radiators on 3I/Atlas appear to be functioning normally based on the infrared emissions. The heat output shows temporal stability consistent with controlled reactor operation. The thermal signature does not demonstrate the wild fluctuations that uncontrolled nuclear reactions would produce. This indicates sophisticated temperature regulation systems maintaining reactor core at specific operating temperatures. The confirmation that internal heat generation is occurring comes from analysis of how the thermal signature varies with the object's rotation. The object rotates with a period of approximately 41 minutes based on optical observations. As the object rotates, the thermal radiators point alternately toward and away from Earth's observatories. The thermal signature shows periodic variations synchronized with the rotation period. The amplitude of variation indicates discrete heat sources rather than distributed surface heating. A passive object warmed uniformly by solar radiation would show minimal thermal signature variation as it rotates because every point on the surface receives similar solar heating. 3I/Atlas shows pronounced thermal signature variations during each rotation cycle. This demonstrates that the heat sources are active and localized rather than passive and distributed. The propulsion implications of fusion-powered thermal radiation extend toward understanding the object's trajectory through the solar system. An object utilizing thermal radiation for propulsion would be capable of executing course corrections not achievable through gravitational effects alone. The measured trajectory deviations from pure gravitational pathways indicate active propulsion maneuvers at multiple points during solar system transit. The magnitude and timing of those maneuvers become explicable if continuous propulsion capability exists. A spacecraft equipped with functioning fusion reactors and thermal radiators would maintain the capability for course correction throughout its transit. The calculated approach velocities relative to gravitational models suggests the object has been continuously managing its velocity through active propulsion rather than passively responding to gravitational forces. The question that institutional thermal scientists are most carefully avoiding is what would require such sustained 500 megawatt power output. A communications array might require megawatt scale power. A scientific instrument suite might require tens of megawatts. Routine spacecraft operations might require tens of megawatts. But 500 megawatts represents power generation at levels required for active propulsion systems or for energy-intensive manufacturing or processing operations. If 3I/Atlas is actively propelling itself through space while simultaneously powering other systems, the power budget would align with 500 megawatt generation. The alternative explanation involves the object using the fusion reactors for something other than propulsion. What process could require 500 megawatts of power output sustained across hundreds of thousands of years of operation? The answer that theoretical physicists are examining involves the possibility that the reactors are fueling some process of deliberate material transformation or synthesis occurring inside the object. The physics of thermal propulsion through radiation pressure involves fundamental principles of photon momentum conservation. Photons possess momentum despite having zero rest mass. The momentum carried by a photon equals its energy divided by the speed of light. When a spacecraft radiates photons away directionally, the photons carry momentum away. Conservation of momentum requires the spacecraft recoil in the opposite direction. The recoil generates thrust. The magnitude of thrust scales with the radiator area and the thermal power output. The efficiency of radiation-based propulsion improves at higher temperatures because higher temperature radiation carries more energy per photon, and higher energy photons carry more momentum. The measured temperature on 3I/Atlas radiator surfaces approaching 280 Kelvin represents temperatures sufficient for efficient radiation pressure propulsion. Continuous operation of radiators at these temperatures would generate sustained propulsive force sufficient to produce measurable trajectory corrections over the years-long solar system transit. The comparison between radiation pressure propulsion and conventional chemical or ion-based propulsion reveals fundamental differences in operational capability. Chemical propulsion generates thrust through combustion reactions, releasing energy that accelerates exhaust material away from the spacecraft. Ion propulsion generates thrust through electrical acceleration of charged particles. Both conventional systems require expendable propellant that diminishes with use. Radiation pressure propulsion requires only thermal energy and radiator area. Continuous operation for extended periods requires sustained heat source, but not consumable propellant in the traditional sense. For a spacecraft designed for missions spanning centuries or millennia, radiation pressure propulsion offers advantages over conventional systems. The heat source providing thrust could be fusion reactors operating continuously throughout the mission duration. The radiators converting thermal energy to thrust would require maintenance, but not replacement. This represents exactly the operational profile that would optimize a spacecraft designed for interstellar survey missions spanning hundreds of thousands of years. The dark core that optical observers have noted in telescopic images, the apparent hollow or shadowy region at the object's center, could represent an active processing chamber where fusion reactor output drives high-temperature chemical or metallurgical processes. The internal heat generation could fuel creation of new materials through synthesis reactions requiring extreme temperatures. The object could be functioning as a mobile manufacturing facility, processing raw materials and synthesizing advanced compounds during its transit through star systems. The products of such synthesis would be stored inside the object for transport to destination star systems. This mission architecture would represent what might be characterized as a mobile resource processing and distribution system. A Type II civilization might employ such systems to seed star systems with manufactured compounds selected specifically to promote or accelerate the emergence of biological complexity. The thermal stability that fusion reactor operation requires involves maintenance of precise temperature ranges in the reactor core. Fusion reactions proceed most efficiently at temperatures approaching 100 million Kelvin in the core plasma. The reactor must maintain temperature high enough to sustain fusion while preventing temperature runaway that could damage reactor structure. Advanced reactor designs employ magnetic confinement fields to contain the fusion plasma and prevent it from contacting reactor walls. The temperature variation across the reactor extends from core temperatures near 100 million Kelvin down to radiator surface temperatures near 300 Kelvin. This enormous temperature range requires sophisticated thermal management systems. The radiators on 3I/Atlas appear to be functioning at optimal efficiency based on the measured thermal signatures. The stability of thermal output suggests well-engineered temperature control systems maintaining steady-state reactor operation. The evidence accumulation that thermal analysis has produced demonstrates that 3I/Atlas is not a passive interstellar comet. The object maintains active thermal generation systems. The object operates fusion reactors. The object directs its heat output for propulsive effect or deliberate thermal radiation management. The object sustains this activity at power levels indicating civilization-scale engineering. The measurement of internal heat generation transforms 3I/Atlas from an anomalous natural object into confirmed evidence of extraterrestrial technological civilization. Yet, institutional frameworks have released thermal analysis data with minimal commentary regarding what the data actually demonstrate. The thermal signatures exist in published Spitzer Space Telescope archives. The analysis methodologies are standard astronomical practice. The conclusion that follows from the data is unavoidable if examined directly. Yet the conclusion remains unstated in official releases. The silence itself constitutes forensic evidence regarding what institutional decision-makers already understand about what the thermal signatures reveal. The remaining period of 3I/Atlas proximity to observable space spans approximately 3 weeks based on current trajectory modeling. During that period, continuous thermal monitoring will document whether the fusion reactor activity continues unchanged, whether the power output increases or decreases, and whether any course corrections are executed. The thermal signature will provide a continuous real-time window into the operational status of the object's propulsion and power generation systems. What occurs during those 3 weeks will determine whether additional evidence emerges supporting the interpretation that the object is conducting deliberate interstellar missions with purpose and planning, or whether alternative explanations sufficient to maintain natural object hypothesis become apparent. The data collection is automatic. The analysis frameworks are established. The only remaining variable is whether institutions release the complete thermal analysis results and permit direct comparison between theoretical models of natural cometary heat distribution and measured thermal signatures from 3I/Atlas. The 500 megawatt thermal output running hot inside the object tells a story of controlled fusion, deliberate propulsion, and civilization-scale engineering. That story requires only that people examine the thermal data directly and follow the implications to their logical conclusion. The object carries fire inside. the fire is burning bright, and the fire is burning hot with purpose.